Welcome again to the lecture series of signals and systems. In the previous lecture, we have seen the concept of foundation for the Laplace transform, the jet transform, and we consider some important examples to clarify the concept of region of convergence in the calculation of determination of the Laplace transform. Now we will consider some more examples as we have seen in the last lecture. The Laplace transform of T ut is equal to 1 upon S. Now find the Laplace transform of, suppose the given signal xt is equal to t square u of t. For this purpose, we will use the relation x of s is equal to limit from minus infinite to plus infinite t square u of t e power minus st. So, because ut is here and this will exist only for the positive values of time, I can put this limit from 0 to infinite instead from minus infinite to plus infinite. So this is equal to t square and this ut will become 1 in this range from 0 to infinite into e power minus st, and this can be determined by this integration can be calculated by using integration by part, which is equal to first function integration of second function integration of this e power minus st by minus s minus integration of differentiation of first function is differentiation of t square, which is nothing but 2t, and integration of e power minus st or minus s. Integration of this gt. This will become t, limit will be from 0 to infinite. Limit will remain as it is. This is t square e power minus st upon minus s t square minus, now this will become minus and this minus I will write it plus, and this will become 2 by s into integration of e power minus st into t dt. Limit will remain as it is from 0 to infinite. Now this will become t square e power minus st by minus s plus 2 by s. Solve this. This will become t into e power minus st by minus s minus integration of differentiation of this function into integration of e power minus st. So this will become e power minus st by minus s dt. Limit will remain from 0 to infinite. Further, this can be simplified as this x of s will be equal to t square e power minus st divided by minus s, t square into e power minus st divided by minus s plus 2 by s into t into e power minus st, t into e power minus st divided by minus s, t into e power minus st divided by minus s, and this will become minus, this integration will give e power minus st upon s square, e power minus st upon s square. Limit is from 0 to infinite. Now, when we will put t is equal to infinite, when I will put this upper limit in place of t, this will become e power plus infinite means e power minus, this will become e power minus infinite means this will become 0. So this is 0 plus, first I will put the upper limit in all the terms. This will become 0. This will also become 0. And this will also become 0 because of e power minus infinite. So all the terms will become 0 and we will put t is equal to infinite. And then minus, I will put minus, and now I will put t equal to 0. This will become 1, I will put t equal to 0. This will become 0 because t square is here. This will also become 0 because t is here. This will become 1 upon s square minus 1 upon s square, and this will be equal to 1 upon s. It means that the Laplace transform of t ut, Laplace transform of t ut is equal to 1 upon s. Laplace transform of t square ut is equal to 2 by s square. Then we can generalize this relation as Laplace transform of t power n ut will be equal to factorial n upon s power n plus 1. Important relation. We have seen these two cases. Laplace transform of t into u of t is equal to 1 upon s. Laplace transform of t square into u of t is equal to 2 upon s square. Then Laplace transform of t power n into ut will be equal to factorial n upon s power n plus 1, where ROC is s should be greater than 0. If s will not be greater than 0, then these relations e power minus st will lead to infinite, and this integration will not converge if the value of s will become negative. So for all these cases, value of s will be greater than 0, and this will be the region of convergence for the given relation. Now consider some more useful cases. Consider some more useful cases for which we cannot find the Fourier transform. Like suppose x of t is equal to e power at u of t. Consider this case. We know if value of a is positive in this case, if a is greater than 0, then this will be an unbounded signal, and for such signals we cannot find out the Fourier transform. Now we cannot find out the Fourier transform, but we can find the Laplace transform of such signals with certain limitations on sigma. So what will be the Laplace transform of this function? This will be equal to x of s will be equal to limit will be from 0 to infinite because ut is here, and in place of xt I will put e power at into e power minus sigma t. In place of sigma t I will write e power minus st directly into dt from the relation of Laplace transform, and this will become integration from 0 to infinite e power a minus s, or we can write it as minus of s minus a t dt. This will become minus of s minus a into dt, and after integration this will become e power minus of s minus a t infinite here. This will become e power minus infinite means 0 minus 1 minus is already there. This will become plus 1 upon s minus. It means that we can find the Laplace transform of this simple e power at, which is not absolutely integrable, but with a certain condition that here this s minus a should be greater than 0. If this s minus a will become negative, then this will become e power plus infinite, when I will put t equal to infinite here. So this term s minus a should always be greater than 0 for the convergence of this integration. So there is a limitation that this s minus a should be greater than 0, or we can say that s should be greater than a. This is the reason of convergence of this given function. Means we can find out the Laplace transform of given signal e power at. Suppose this is the value of a. We can find out the Laplace transform of this signal e power plus at ut only when the value of sigma is greater than a. Means in this region only. Means this signal can be converted in the frequency domain only when the value of sigma will exist in this region only, or sigma greater than a only. For the remaining values of sigma, this integration is also not integrable. So we can integrate this function only when the value of sigma is greater than a. This is important relation. Remember this as it is. Now consider another example. E power minus j omega t. Suppose xt is equal to e power plus j omega t ut. We can find the Laplace transform with standard given relation. Laplace of xt will be equal to, this will be from 0 to infinite, e power j omega t into e power minus st dt. Or we can write it as e power minus s minus j omega t dt, where limit is from 0 to infinite. Or we can write it as e power minus s minus j omega into t divided by minus s minus j omega, limit is from 0 to infinite. And this will become, when I will put t equal to infinite here, this will become 0. And when I will put t equal to 0 here, this will become 1 upon s minus j omega. 1 upon s minus j omega. But with the certain condition that this s should be greater than 0 here. This s should be greater than 0 here, because this is the real part. This will become minus s minus j omega, can be written as minus sigma plus j omega minus j omega, means it is e power minus sigma t. For that purpose, for the existence of this integration, this sigma should be greater than 0. And that is the reason of convergence for this given relation, that this s should be greater than 0. So the reason of convergence for this equation will be all the positive values of sigma. This is the reason of convergence. So the Laplace transform for e power j omega t, Laplace transform for the e power j omega t will be equal to 1 upon s minus j omega. Laplace transform of this signal e power j omega t ut will be equal to 1 upon s minus j omega. Similarly, we can find the Laplace transform of e power minus j omega ut, and this will be equal to 1 upon s plus j omega. As we have seen, the Laplace transform of signal e power j omega t ut is equal to 1 upon s minus j omega. Similarly, the Laplace transform of the signal e power minus j omega t ut will be equal to 1 upon s plus j omega. And by using these two relations, we can find the Laplace transform of cos of omega t ut. We know that the signal cos of omega t can be written as cos of omega t is equal to e power j omega t plus e power minus j omega t divided by 2, and sin of omega t can be written as e power j omega t minus e power minus j omega t by 2j. So by using these relations, we can find the Laplace transform of the signals sine and cosine. So the Laplace transform of cos of omega t will be equal to Laplace transform of e power j omega t plus e power minus j omega t divided by 2, or this can be written as 1 by 2 Laplace transform of e power j omega t plus Laplace transform of e power minus j omega t, or this is simply can be written as 1 by 2 Laplace transform of e power plus j omega t will be equal to 1 upon s minus j omega, 1 upon s minus j omega, and remember, region of convergence for this will be equal to s greater than 0 plus Laplace transform of e power minus j omega will be equal to 1 upon s plus j omega, where s should be less than 0. And after simplification, we can write it as 1 by 2. This will become s plus j omega plus s minus j omega divided by s minus j omega into s plus j omega. Further, this can be simplified as this j omega and this minus j omega will get cancelled. This will become 2s 1 by 2 into 2s upon s square minus j omega whole square, and this will become equal to 1 by 2 into 2s upon s square minus this j square omega square will become minus omega square, means s square plus omega square, and this 2 and 2 will get cancelled. This will become s upon s square plus omega square for all values of s. So by using these two standard relations, we can find the Laplace transform of cos of omega t as s upon s square plus omega square for all values of s. And similarly, we can find the Laplace transform of sine of omega t by using this relation given. So the Laplace transform of sine of omega t will be equal to Laplace transform of sine of omega t will be equal to Laplace of e power j omega t minus Laplace of e power minus j omega t divided by 2j, or simply this can be written as 1 by 2 Laplace of e power j omega t, this is 1 by 2j, minus Laplace of e power minus j omega t, or we know that Laplace transform of e power plus j omega t is equal to 1 upon s minus j omega minus 1 upon s plus j omega, and this will be equal to 1 upon 2j. This is s plus j omega minus s plus j omega divided by s minus j omega into s plus j. This s and s will get cancelled, and this will become x of s is equal to 1 by 2j into, here it is j omega plus j omega, this is 2j omega divided by s square minus j omega square. This 2j and this 2j will become cancelled. This is omega upon s square plus omega square. This is the Laplace transform of the sinusoidal signal sine of omega. Very important lessons these are. The Laplace transform of e power at is 1 upon s minus a. Laplace transform of e power j omega t is equal to 1 upon s minus j omega. Laplace transform of e power minus j omega t is equal to 1 upon s plus j omega. And Laplace transform of cos of omega t is equal to x upon s square plus omega square. Laplace transform of sine of omega t will be equal to omega upon s square plus omega square. So these are some important lessons. We can directly utilize these relations to get the Laplace transform of a given sequence, or similarly we can find out the Laplace transform of a given sequence e power minus at also, and this will be equal to 1 upon s plus a. Now find the Laplace transform of find the Laplace transform of, suppose xt is equal to minus of e power minus at u of minus t. We have to get the Laplace transform of this signal by using the given relation of the Laplace transform. And we know first we have to define this function u of minus t, because ut is equal to 1 when t is greater than or equal to 0, and this will be 0 when t is less than 0. Then u of minus t will be equal to 1. In place of t I will write minus t here when minus t is greater than or equal to 0, and it is 0 when minus t is less than 0. This can be written as t should be less than or equal to 0. Here t should be greater than 0. Means the given signal u of minus t will exist only for the negative values of t, when t will be less than or equal to 0, and this will become 0 when t is greater than 0. So I will write the limit here. From now I will write the limit in the relation of Laplace transform from minus infinite to 0, because this signal u of minus t will exist only for this region, t less than or equal to 0. And now this will become minus e power minus at into e power minus st dt. Now this will become minus of integration from minus infinite to 0 e power minus s plus a into t dt, or I can write it as minus of its integration will be e power minus s plus a upon into t upon minus of s plus a, limit is from minus infinite to 0. Now when I will put upper limit here, means when I will put t equal to 0 here, this will become minus 1 upon s plus a. So this will become, when I will put t equal to 0, this will become minus is already here outside of the bracket, minus 1 upon s plus a minus, and 1 minus is already here, this will become plus. When I will put minus infinite, this will become infinite, because 1 minus is already here. I will put minus infinite, this will become e power plus infinite, and this relation, this integration will give an infinite value. So value of this integration will become infinite when this s plus a is greater than 0. If we want to convert this integration, for that purpose this s plus a should be less than 0. When this s plus a is less, will become less than 0, when this s plus a will become less than 0, this value will become negative, this will become negative, and this negative will become positive, and when I will put t equal to minus infinite here, again this will become 0. So this will converge only when this will be equal to s plus a, only when s plus a is less than 0, or we can say that s is less than minus. This is the reason of convergence for this equation. Now consider another case. Remember this case when e power minus at u power minus t, Laplace transform of this function will be equal to 1 upon s plus a, with reason of convergence s should be less than minus. Now consider another case where xt is given as e power at ut. Xt is given as e power minus at u of plus t. So Laplace transform of this signal will be equal to integration from 0 to infinite. Now because this is ut, so limit of integration will become from 0 to infinite, because ut will exist only for the positive values of t, and this will become e power minus at e power minus st dt. This is equal to e power, integrate this function from 0 to infinite, e power minus s plus a into t dt, and this will be equal to e power minus of s plus a into t upon minus of s plus a 0 to infinite, and this will become, when I will put t equal to infinite here, this will become e power minus infinite, but this will become e power minus infinite only when this given value s plus a is greater than 0. Greater than 0. Only when this value is positive, we can put t equal to infinite, and this will become e power minus infinite, means this will become 0 minus 1 minus is already here, this will become plus e power 0 upon s plus a, means 1 upon s plus a. Again, here the region of convergence is S should be greater than minus. If we will see the Laplace transform of these two equations, one is minus e power minus at u of minus t, and here is a function u of e power minus at u of t. For both these functions, Laplace transform is same. For this function, Laplace transform is 1 upon s plus a, and for this function also, the Laplace transform is 1 upon s plus a. So we cannot discriminate. Here is a complexity in finding the Laplace transform of such type of signals. But there is a speciality of this Laplace transform. This is the region of convergence. Although the both these two terms are same, 1 upon s plus a and this is also 1 plus a, but the region of convergence is different. This will exist only for s is greater than minus a. Means, suppose here is a value minus a, suppose a is a positive value. So minus a will be somewhere like this. Suppose minus a is here. So this Laplace transform will exist only for s is less than minus. Means this will exist only in this region. Whereas this Laplace transform of e power minus at ut will exist for s is greater than minus a. So although these two terms are same, but their region of convergence are different. This is the speciality, or we can say this is complexity also in the Laplace transform. But there are more advantages of using Laplace transform than this complexity. So this is one case where the importance of the region of convergence comes into the picture. That two different functions may have the same Laplace transform, but their region of convergence will be different. This is the speciality of this. This is the importance of this region of convergence. This can discriminate the Laplace transform of two different functions, even if they both functions have the same Laplace transform. So this is all for this lecture. In the next lecture, we will discuss more about the region of convergence of the Laplace transform. Thank you.